Hello everyone, this is topic 10 of exam 3, method of partial fractions, or last case, irreducible quadratic factors. So as we talked about before, irreducible quadratics, or quadratics that are not factorable, the way we typically will see them is of the form of a sum of two squares, like for example x squared plus 25. So we know we can factor the difference of two squares, but not the sum of two squares. So a little remark, when dealing, we have to include, with these types of factors, we have to include all possibilities that may make the fraction proper. So here's just an example illustrating that concept. So remember, you're going to have as many, in the decomposition here, you're going to have as many fractions as you have unique factors in the original fraction. So in this case, one with an x in the denominator and one with that irreducible quadratic x squared plus 1. What goes above the x, as we've seen before, because it's linear, is just a constant term, so we'll call it a. But what goes above the x squared plus 1, because we have to include all possibilities that could make it proper, I can't put an x squared up there, but I could certainly put an x there. So let me call it bx, but then I have to include a constant as well. So bx plus c. So essentially, whenever you're dealing with an irreducible quadratic, in the numerator of the decomposition, you have to include both a linear term and a constant term. And then here's just another example with repeated factors involved as well. First off, we have x cubed. And as we've seen, you're going to have three fractions then, because it's a power. And the first fraction, the unique factor of x raised to the first, or just x. Next fraction, x squared. Next fraction, x cubed. What goes above each is whatever makes the unique factor proper. The unique factor is linear, so just constants. So a, b, and c above each of those. And then we have this irreducible quadratic that's raised to a power, and it's being squared, so we're going to have two fractions from that, one with x squared plus 9 to the first, or just simply x squared plus 9, and then another with x squared plus 9 as a quantity squared. But what goes above each of those is whatever makes the unique factor proper, and the unique factor is now an irreducible quadratic. So as we did here, you have to include both a linear term and a constant term. So since we left off with c, let's say dx plus e, and consequently fx plus h. Okay, so that's how we deal with irreducible quadratics. So a formal example now. It's already factored for us. Note the irreducible quadratic. Could start with the partial fraction decomposition. Take out the integrand, x plus 2, over x squared plus 1. That's going to be equal to, okay, coming from the x, we'll have one fraction with just a constant in the numerator. Coming from the irreducible quadratic, x squared plus 1, one fraction, but because it's an irreducible quadratic, a linear term and a constant term. So we'll call it bx plus c. We continue as normal, create the working equation. We're multiplying by the least common denominator, which is the denominator on the left. And so on the left, we just get the numerator, x plus 2. When we multiply a over x by that denominator, the x's cancel. And we're left with a times the quantity x squared plus 1. Okay, here's something important here. This bx plus c is a binomial quantity, so you have to put parentheses around that. And then multiplying that fraction by this denominator, the x squared plus 1's cancel, so we're just left with x. But again, parentheses are imperative here. Okay, so then we could use the elimination method. We can cause this to be 0 by letting x equal 0. And on the left, we substitute 0 for x, so 0 plus 2 equals a times 0 squared plus 1. No need to substitute a 0 in here because x is a factor And if x is 0, those terms go to 0. So immediately we get that a is 2. Okay, now there's no other real numbered value of x that we could choose that's going to allow us to use the elimination method. There is a number, and I'm going to show you after we're done with this how you could use the number that I'm thinking of to cause this to be 0, but there's no real number. So only other method, comparison. So let's compare, let's say, alright, we want to find b, so let me think about b is associated with an x squared. So compare the x squareds. On the left we have 0x squared. On the right there's an ax squared and plus a bx squared. And if you wanted to, as I've mentioned in the past, I mean, you should be able to just pick them out by inspection. But if you wanted to literally distribute here, and then look at the like terms, that's fine as well. However, you get there at that point, divide out the x squareds. 0 is a plus b. Fortunately, we know a. And so 0 is 2 plus b, and b is negative 2. Okay, only thing left to solve for is c. And just think about what c is involved with. Again, if you didn't distribute, you could see the only thing c is involved with is an x. So compare the x's. And so on the left we have 1x, or just simply x. On the right, the only thing associated with an x is the c. And so dividing out the x's, we get c as 1. Okay, so now this original integral, the integral of x plus 2 over x and x squared plus 1 is now equal to, by the partial fraction decomposition, okay, we're going up here, and we're replacing a, b, and c respectively by the values we found. So we have a over x, or 2 over x, and then plus bx. B was negative 2, so minus 2x plus c plus 1 over x squared plus 1. And that's all with respect to x. And now something interesting happens. We're going to separate this. You can think of separating it into two integrals, but let's think about this before we do. The first integral is not going to be a problem because you could factor out the 2 and you're left with the integral of 1 over x with respect to x, which certainly we should know what that is. But now think about dealing with this fraction. Whenever we consider integrating a fraction, if the denominator is not a power, like we have here, we consider du over u. And it is going to work partly, because if you consider the integral of du over u here, which of course results in the natural log of the absolute value of u, we'd be taking u to be this denominator x squared plus 1. Well, its derivative, knowing the du has to be satisfied, of course, is 2x. And we do have the 2x in the numerator that is going to help to satisfy the du. But we have this extra term, this extra plus 1 term. So what we're going to do here is split this integral up at that point, so that we'll now have, now I'm going to leave the 2 in there just to be a little bit clever. So I'm going to make it 2x. I'll factor out the negative from the 2 over x squared plus 1 with respect to x, and then splitting the integral plus the integral of 1 over x squared plus 1 with respect to x. And at that point, we can consider a u substitution on the second integral. First integral we know we're satisfied with because that's the natural log of the absolute value of x. But now dealing with the third integral. Well, here's a situation that you have to recall from previous exams, exam 2 in particular, where du over u doesn't work. And we said if du over u doesn't work, then we turn our attention to the integrals that result in the inverse trig functions. And in particular here, I'm kind of isolate these sideline stuff. What we're dealing with is the integral of u squared plus a squared in the denominator, which results in 1 over a inverse tangent of u over a, plus or constant. And in this particular case, if you consider u squared plus a squared, u is x squared and a squared is 1. Or excuse me, u squared is x squared. So that means that a is 1 and that u is x. And the du is just 1 dx. So there's really no need for a modification by a constant multiple. And there's no need for a formal u substitution because the 1 dx identically satisfies our du. So what I'm saying is, by inspection here, you can consider that the integral without a u substitution, the integral of 1 over x squared plus 1, results in, well, if a is 1, that's 1 over 1. Inverse tangent u is x, a is 1. That's just the inverse tangent of x. So if you have to make the formal u substitution, fine, but I'd like you to consider doing that one by inspection. And similarly here, the reason why I left the 2 in there, okay, here I'm trying to fit du over u though, and I'm taking u to be the denominator, and the 2x dx, that's the reason why I left the 2 in there, because the du is identically 2x dx. So doing those integrations by inspection, we get 2 natural log absolute value of x minus, this just becomes natural log absolute value of its denominator, and then as we just discussed, the inverse tangent of x, and then plus or constant. Okay, so whenever you're dealing with these irreducible quadratics, ultimately you will have a need for the formula that results in the inverse tangent. And one other thing to mention about this particular problem, when we got to this point where we had the working equation and we used the elimination method, we started the comparison method. But there is one other way to solve for the constants. If you consider, let's say you would go through the same process to begin with. You form the partial fraction decomposition, which is the same thing. So a over x, and then plus bx plus c over x squared plus 1. You'd get the working equation. So x plus 2 equals a times the quantity x squared plus 1, and then plus as a quantity bx plus c times x. And you would do the elimination method, let x equal 0. And we got 0 plus 2 equals a times 0 squared plus 1, so a was 2. But now what you could do, instead of the comparison method, as I was mentioning earlier, there is a number that does cause this x squared plus 1 to be 0. It's not a real number though. So here you actually have to use your imagination, because the number I'm talking about is I. which is the square root of -1, our imaginary unit. And I squared is -1. So if we let x equal I, let's see what happens. We get on the left I plus 2. On the right, a times I squared plus 1. And then plus bi plus c times I. But I squared plus 1 goes to 0. Because I squared is -1. So we have I plus 2 is, let's distribute this I. We get bi squared plus ci. But then bi squared is -b. So I plus 2 equals -b plus ci. And you still have to compare. But now what you're comparing is the imaginary unit. And on the left we have 1i, on the right ci, so c is equal to 1, and then you're comparing the real numbers, the real parts, and that on the left is 2 equaling -b, and so therefore b is -2. So if you like working with the imaginary, and you can see, of course, those are the same values that we obtained with the comparison method. So if you want to use the imaginary unit, that's fine. I know some students steer away from it, so I'm probably going to stick to the comparison method. And I'm going to cut this video off right now. We've got 2 more examples. Hopefully we'll be able to finish them in one taping, and so we'll see you back when you're ready.